Hi guys, let's see the one more applications of dimension analysis. It is to check the dimensional correctness of a physical quantity. So in the previous application we learned that the dimensional analysis help us to convert a physical quantity from one system of units to another system of units. So to do this, we need to depend upon a formula. So this formula you please remember. So for one system of units to another system of units. So then we can easily convert that dimensions. But this the second application, that is the system of to check the dimensional correctness of a physical quantity, whether the physical quantity is dimensionally correct or not. So to understand this, let me take an example. So that example is, let me take a equation, well-known equation, displacement s equal to ut plus half at square. So this is the second equation of motion. Now, if I write the dimensions, so s is a displacement. So displacement we are measuring in terms of length. It is displacement. So displacement units are nothing but L. Since this equation contains equal, so each term should have same dimensions. If S is term contains dimensions of displacement, means L, the term ut, so ut also should have same dimensions, and half at square also should have same dimensions. Then only there is a meaning of this equal. If they both are not having the same dimensions, so this equation is incorrect, dimensionally incorrect. Let us check that first. If you can write u is the initial velocity, so velocity units are meter per second, and t is the time units are second. The seconds gets cancelled, we will end up meters, and meters dimensions are nothing but L. And to check half at square, half is a constant do not have dimensions. And for acceleration, that is meter per second square, and time units are second and become second square. Now second square gets cancelled, we will end up meters, so it is also having dimensions L. Now if you can see, all three terms, S is also having same physical quantity, it is also having L, and ut is also having same physical quantity, and half at square, all three terms are having same physical quantities. So it is L, and it is L, and it is also L. So if these three physical quantities, these three terms at here are having same dimensions L and L and L, so we can say this formula is dimensionally correct. Dimensionally correct, this formula. So this is how the dimensional analysis help us to check the formula is correct or not. Let us take one more example. So let me solve the third equation of motion, which you already know. V square minus u square equal to 2as. Now this is also having three terms, and if it is having three terms, each term should have same dimensions. Each term should have same dimensions. Now if you can write v square dimensions, velocity, it is nothing but the dimensions of v, velocity is nothing but meter per second, and here square is there, we need to square that. So I can get meter square upon second square, its dimensions meters means nothing but L square, upon t square, which is equal to L square t power minus 2 is the dimensional formula. Similarly, u square is also a velocity, its initial velocity. Velocity units are meter per second. So we can get here the u square is there. So that's why we need to square at here. So here I can get the same repeated as same m square by s square. So L square upon t square, you can end up with L square t power minus 2 is the dimensions for u square. Now let's check the dimensions for 2as. For 2as, 2 is a constant, it do not have any dimensions. And acceleration means nothing but meter per second square. So that is the units for acceleration. And yes, here the s means nothing but the displacement. Displacement having units meter. And if I simplify that, it will becomes m square upon s square, which also equal to L square upon t square in terms of units. It also equal to L square upon t power minus 2. Now these three terms are having same dimensions. So if these three terms are having same dimensions, we can say the formula is dimensionally correct. So this kind of analysis we can do with the help of dimensional analysis to check the dimensional correctness of a physical quantity. So this is the second application of dimensional analysis. Now it's also having one more applications. Let's see that the third application. The third application is to derive a relation. To derive a relationship between different physical quantities. To derive a relationship between different physical quantities. So we need to derive a relationship different physical quantities. So let us see how this dimensional analysis help us to derive relationship between different physical quantities. Let's take an example. So with the help of example, I would like to elaborate much more. The example is, let us derive an expression for the centripetal force. Centripetal force capital F, which is acting on a particle of mass, which is acting on a particle of mass small m moving with velocity v in a circle of radius small r. So a centripetal force which is acting on a particle of mass small m, and the particle is moving in a velocity v and moving in a circle of radius small r. So this is situations which is a force if an object moving in a circular path. The circular path having the radius r. If this object is moving in a circular path, on this object centripetal force will be there. Now if we take that force is directly proportional to mass and that force is directly proportional to velocity and that centripetal force is directly proportional to radius. So we combine this expression and we will rewrite. Before that, so if it is having any powers, let me take that as m power a and v power b and r power c. So here a, b, c are certain powers. We need to find it out what are these powers values are. You will understand why I have taken a, b, c in ahead. So if I write this expression all together by taking out the proportionality constant, therefore f equal to k times m power a and v power b and r power c. So here the k is proportionality constant. So this constant do not have any dimensions, so we can take that value goes as 1. Now this formula we can rewrite as f equal to m power a k times and v power b and c and r power c. Now I know the dimensions of force. What are the force dimensions I can write? It's m l t power minus 2. Now which is equal to, now if you can take k value equal to 1, the constant, it's 1 of m is a mass. So mass we can write m power a and v is the velocity. So velocity dimensions l t power minus 1 power b and r is radius. Radius means nothing but distance, that gives l power c. Now on the right side it is equal to same m l power t power minus 2, but on the left side if we can simplify again, it becomes 1 as usual m power a and here becomes l power b and t power minus b and again l power c. Now m l t power minus 2 which equal to, on the left side if you can make it equal, it's m power a and here we are having the two length terms. So we can combine that equation, l power b plus c and third that equal to t power minus b. Now on the both sides if you can make equal the corresponding powers, if the a, here the corresponding power for the a where nothing is there, we can take it as 1. Therefore I can write that a value equal to 1 and the second term if you can compare the length l, on the left side it is equal to b plus c, on the right side here nothing is there, its value equal to 1 and the third side here equal to minus b which equal to minus 2. So here on the 3 powers we compare to on the 3 powers on the other side. Now if you can do further simplification of these calculations, so from this expression I can get, so let me take this as equation 1 and 2 and 3. Now from 3 minus gets cancelled, therefore b equal to 2. If you can substitute b value in equation 2, so therefore 3 into, so I can get that 2 plus c equal to 1, therefore c equal to minus 1. So we got the value of c which equal to minus 1. Now a value is already minus 1. Now if you can write that separately, a equal to 1 and b equal to 2 and c equal to minus 1. Now these expressions, these corresponding values, if I can substitute in the very standard equation which I have taken. So this is the standard corresponding equation which I have taken. Now if you can substitute those values at here, the formula changes. F equal to k times m. In the place of m power value, a value goes to 1 and b value goes to here the 2 and c, the value of c, it gives to me that minus 1. So c value are power minus 1. Since a equal to 1 and b equal to 2 and c equal to minus 1. If we can rewrite this formula, so that is equal to k times m, v times becomes v square times r power minus 1. So f equal to k times m v square by r. So this is the formula of centripetal force. Now we derived the centripetal force formula by taking an expression, by considering an expression that the force is proportional to mass and proportional to velocity and proportional to radius. Now here we compared that dimensions what we have taken. So this is the corresponding comparison with the dimensions of the force. So the dimensions of the force at here. Now this is how it will help us to bring the final expressions in terms of length, mass and time. Finally we are able to derive that centripetal force. So this is how the dimensional analysis is help us to derive the relationship among physical quantities.